So this is a continuation of our lesson on January 22nd. We have already done a video talking about the properties of metals and metallic bonds, and we have also talked about the electronegativity differences for ionic and covalent bonds. So this video is going to talk about the octet rule, Lewis dot diagrams, and an introduction into ionic bonding. So that is all we have for the electronegativity differences. So now we're going to look at something called the octet rule. Okay, to understand why chemical bonds occur, we need to know the rule of octet. Okay, and most of you are probably thinking octet. Oct comes from like the word octagon. What does that make you think of? 8. Okay, that's going to be very important. So what are valence electrons? We already defined this earlier. We've defined this multiple times, but we're going to define it again. Valence electrons are electrons within an atom that can participate in the formation of a chemical bond. They are located in the outermost energy level. So how do we determine how many valence electrons an atom has? We've talked about it in this class. We look at the periodic table. If they are in the group the element is found in on the periodic table, tells us how many valence electrons it has. If it's in group 1, it has 1 valence electron. That's the first column. If it's in group 2, it has 2 valence electrons. Then we jump over to boron's group, 3A, on your periodic table. That's the third group. It has 3 valence electrons. And you can see the pattern continuing till we get to the noble gases, which have 8 valence electrons. How many electrons does it take to fill a valence shell? Each valence shell needs 8 electrons, like a noble gas. The s and p orbitals must be filled. We have 2 electrons that go in the 1s orbital, and we have 6 electrons that go in the p orbitals, 2 in each of the 3 p orbitals. So 2 plus 6 give us the 8 total valence electrons. Which elements don't follow the octet rule? There are a few that do not follow this rule. They require fewer than 8 to fill the valence shell. Well, if you remember when we talked about orbitals, the first 2 energy levels only have an s orbital, which is one orbital that can hold 2 electrons. So the first energy level has 2 valence electrons, and then it moves on to the second. So this affects hydrogen and helium, the 2 elements that only their valence electrons are located in the first energy level. Okay, so hydrogen and helium do not follow the octet rule. Now, if you notice right here, there are other exceptions to the octet rule that we will discuss later. The next thing we're going to talk about is Lewis dot diagrams. I have been told that if you went to collegiate in middle school, I believe you've learned this. So if you have and you feel very comfortable, you can fast forward through this part. But anyone who needs a little refresher, here we go. These are helpful in visualizing the electrons in a chemical bond. To draw a Lewis dot diagram for an element, here are the steps. Use the chemical symbol to represent the element's nucleus and core electrons. Okay, so we are going to draw the chemical symbol, like H for hydrogen or Be for beryllium, and it represents the nucleus of that atom and any non-valence electrons or core electrons. Then we're going to use dots around the 4 sides of that symbol to represent the valence electrons for the element. If the element has more than 4 valence electrons, we place 1 dot on each of the 4 sides before we add a second dot on any side, and any one side can't have more than 2. Which rule or principle does this represent from orbital diagrams? If you remember, we had 3 rules from orbital diagrams, and one of them said that we have to fill each orbital with 1 electron before we start double filling. And if you remember, that was Hund's rule. Ms. Wyrens likes to think of that, if you remember, as the sleepover rule. If you have 3 beds in a house, 2 people aren't going to sleep in 1 bed if there's an empty bed available. So that helps us follow Hund's rule. The dots without pairs usually represent electrons that will form bonds. So if we have any electrons that don't have like a buddy, that it's a side of the element symbol that does not have 2, that dot represents an electron that's usually going to form some kind of bond. Alright, so let's do a few examples. If we have sodium, if we look on our periodic table, it is in group 1. It's It's in the first column. That means it has one valence electron. So this one's really easy. We just draw one dot on one side of the atom. It does not matter which side that dot is drawn on. Okay? The next one we're going to look at is phosphorus. It is in the fifth group. Okay, the fifth column under nitrogen. That means it has 5 valence electrons. If you remember from our rules, it says if we have more than 5, we have to put 1 on each side, as I'm doing right now. And then we can put the fifth one anywhere. It's going to double up with somebody. So if you notice, we have 3 sides that just have 1 and 1 side that has 2. Moving on to oxygen. Oxygen is in the sixth group, so it will have 6 valence electrons. So we do 1, 2, 3, 4, all on different sides, and then we can pick any 2 sides to put the remaining 2. Okay, so we have 2 sides with 2 and 2 sides with 1. Calcium has 2 electrons, so it will have 2 on any 2 sides. They just can't be on the same side. Okay, neon, it has a full outer shell. It has 8 electrons because it's in the noble gas. It's in the 8th group. So we do 1, 2, 3, 4, and we still have to do 4 more, so we buddy up every one of those guys. So this will have 2 on every side. This is the maximum you can have on any of the Lewis dot diagrams. Chlorine is in the 7th group. It should have 7. So we'll do 1, 2, 3, 4. Okay, and then we need 3 more. So 1, 2, 3. Okay. If you would like, you can try the last 2 on your own. You might have been doing that already. But if you would like to pause the video, complete the last 2 on your own, and then you can come back and I will explain the last 2. So aluminum is in the 3rd group. It needs 3 valence electrons. So we have 1, 2, 3, all on different sides. Carbon is in the 4th group. It needs 4 electrons, so we just give them 1 on each side. 1, 2, 3, 4. Okay, you do have your homework assignment does cover this. The front page of your homework asks you to complete these Lewis dot diagrams for different elements. It'll ask you how many valence electrons and to draw the Lewis dot diagram. Okay, moving on. All right, now we're going to do a little introduction into ionic bonding as a whole. We briefly talked about electronegativity difference for ionic and covalent bonding, but now we're going to go deeply into ionic bonding. A quick definition of ionic bond, it's a chemical bond resulting from a transfer of electrons. If you remember, the electronegativity difference was going to be very big. We're going to give you a value for that. If the electronegativity difference is greater than or equal to 2, and we will give you numbers, we're not expecting you guys to memorize the electronegativities of certain elements, but we might give you the numbers. And if the difference between the 2 numbers is greater than 2, that is big enough that it's going to be an ionic bond. Okay? And you can look up the electronegativities of certain elements online. So, if we have this high electronegativity difference, that means one wants electrons a lot more than the other, so it's going to take. That's where we get that transfer of electrons. So here's our definition. One atom is more electronegative than another, so it acquires the other atom's valence electrons in order to fill its outer or valence shell. Electrons from the low electronegativity to the higher electronegativity. So the electrons go from the low electronegativity atom or element, but atom, to the high electronegative atom. Okay? The atom that acquired the electrons, if you acquire electron, you now become negative. You are an anion, and it leaves the other atom. If they lost an electron, they are now positive and a cation. So if you now have a positive and a negative ion, those are opposite charges, they are going to attract. So let's look at an example given the electronegativity. So if we know that the electronegativity of sodium is 0.9 and the electronegativity of chlorine is 3, we calculate what is the delta. That triangle is a delta symbol. That means change in. So what is the change in or difference in electronegativity of NaCl? Well, we take 3 minus 0.9, we get a 2.1. If you remember, in our notes it said if the difference is greater than 2, it's ionic. So because this electronegativity difference of 2.1 is greater than 2, it is ionic. Okay. Now, obviously, if we gave you a question like this on the test, we wouldn't tell you that it was sodium and chlorine, okay? Because from our naming, unit, you learned that Na and Cl, a metal and a nonmetal, are ionic. So we would just give you like these numbers and expect you to calculate the difference and know that that would be ionic. Okay? Forming ionic compounds. So the structure of ionic compounds is they contain cations and anions held together by ionic bonds. We sometimes can have monatomic ions, so we have cations and anions. Sometimes those ions that we're dealing with can be monatomic. Mono or mana is the prefix meaning one, and atomic comes from the word atom. So one atom. So they are ions made up of one atom. So example would be sodium plus, nitrogen 3 minus. Notice all 4 of these examples just have one element or one atom. Polyatomic ions, which you know what these are because you remember them from naming, but why are they called polyatomic? Well, poly means more than one, atomic means atom. So they are ions consisting of more than one atom. So 2 or more atoms which are covalently bonded together that have an overall charge, often negative. If you remember, we do have one that we deal with in our class that's ammonium, and it is positive, and these others, notice they have more than one element, and they are negative. Okay, so ions with more than one atom making them up. Okay, it is important too to remember these ions themselves are held together covalently, but if one of these bonded with another ion, okay, that would be an ionic bond. So you can have both, but we'll talk about that probably a little later. All right. The last thing we are going to do today is use Lewis dot diagrams, which were those things where we had the element and we put dots around them to represent ionic bonding. We must represent all 3 parts of the explanation definition. If you remember, the first part of the definition said there's a transfer of electrons. We are going to represent this by curved arrows from the electrons on the less electronegative atom. Okay, that'll be the one further to the left on the periodic table, or further down, to empty spots on more electronegative elements. Those will be the ones further to the right and higher up. We do not draw the electrons where they've moved from. We just draw an arrow from the electron we're taking to where it's going to go. They form cations and anions. So we're going to draw a big arrow. It's like a double equal with an arrow, and you'll see when we do an example to show the formation of what we end up with after those arrows and the transfer takes place. On the right side of the arrow, we will draw atoms with electrons and charges they end up with. So the atoms will draw their electrons by dots, like a Lewis dot diagram, and the charges they end up with will represent on the top of them. And again, you'll see that in the example. We also know that opposite charges attract. That was the third part of the definition. So when we do number 2, when we write on the right side of the arrow what atoms we end up with, we need to make sure they alternate. That the charges, if we have a positive ion and then a negative ion, that we alternate positive, negative, or negative, positive, so that no 2 like charges are adjacent because they would repel. The reason they're held together in a bond is because they're opposite charges and they'll attract. Again, you'll see this in the next examples. All right, so the first example we're going to do is Na and Cl. The first thing we will do is we will draw their Lewis dot diagram. So if we have sodium, if we look, it is in the first group, the first column, so it is going to have 1 valence electron. Okay, then we look at chlorine. It is in the 7th group, the 7th column, so it's going to have 7. So we do 1, 2, 3, 4, and then we fill in the next 3. 1, 2, 3. Okay. Now, which one of those is less electronegative? That's the one further to the left or further down. That's sodium. Sodium's all the way on the left side. We also, kind of one of the ways we talked about it in class was sodium only has 1. So the only way it can get to a full outer shell is to either lose 1 or gain 7. It's obviously a lot easier to lose 1. Chlorine, on the other hand, can either gain 1 or lose 7. Again, it's a lot easier to gain 1. That's another way you can remember. So we're going to draw arrows showing where those electrons are going to go. The more electronegative chlorine is going to take the sodium electron and put it in its last little place. So we have the arrow going from this electron to this empty spot right here. Okay. Now, if you notice, all of our electrons are accounted for. This one's moved. Now he has an empty original valence shell, meaning the previous energy level's valence shell is now full. And the chlorine just filled his last spot, so he has a full valence shell. So these are now both happy. We draw a double-sided arrow. This is what we were talking about. So now we draw what the atoms look like now. Okay, we have a sodium, and it has no electrons in that original valence shell. This implies that its previous the inner shell, which is now its valence shell, but not its original valence shell, is full, and it has a +1 charge because it lost 1 electron. Now we have chlorine. It now has a full outer shell. Notice it has all 8 dots. It gained an electron, so it has a negative charge. Since we only have 2 ions in this one, it doesn't matter which one's on which side, because if there's only one of each, they're opposite charges and they're going to attract. We won't have any repulsion for that example. Okay. I do want to show you that you would have known it was 1 sodium and 1 chlorine anyway. That's because we learned in the first unit that Na being the first column, we wrote a +1 up there, so it's a plus. Cl is in the 7th column, that's a -1. And to write that, if we were naming that, we would do NaCl to balance those charges. So NaCl implies by the implied subscript of 1, implied subscript of 1, we were going to have 1 sodium and 1 chlorine, and this is what they look like. Okay, this right here is what you do for Lewis dot diagrams and ionic bonding. This is me showing you naming ionic compounds or writing the ionic formula. Okay, the next one we're going to do is calcium and fluorine. Calcium is in group 2, so it has 2 dots, 2 valence electrons, one on 2 different sides. Okay, fluorine is in the 7th group, so it'll have 7. It'll have 1, 2, 3, 4 on each, 1 on each, and then we fill in 3 more, leaving this one side with 1 empty one. So he wants to gain 1, he wants to lose 2. Those numbers don't work out. So we'll just get started and we'll see what happens. So calcium has a low electronegativity. It's going to lose its electron to this fluorine and go there. But if you notice, this fluorine is now filled, so he's good, but this calcium still has 1 electron left. So what we need is another fluorine to give that calcium electron a place to go. So by adding another fluorine, we can now take this extra calcium electron and it will go to this vacant space on this fluorine. Okay, so you can add calciums and fluorines as you need them. Now if you notice, this fluorine has 8, this calcium lost the 2 that it wanted and now has 8 in its previous, in its inner shell, and then this fluorine now has 8. So we are good. So double-sided arrow, here's where we really need to pay attention and make sure we are alternating. So we want to go alternating charges, so the fluorine will come first. It gained 1 electron, so it has a minus charge. The calcium lost 2 electrons, so it has a +2 charge. Notice it doesn't have any dots because it lost all of its original valence shell dots. And the fluorine, the other fluorine down here, gained 1, so it also has a minus. Okay. This question down here asks, what must the ratio of calcium and fluorine be in order to satisfy the rule of octet? Well, we have 2 fluorines for every 1 calcium, so we would write the ratio like that, 1 calcium for every 2 fluorines. But again, if we look at what we learned when we were doing naming, calcium was in the 2nd column, that would have been a +2. Fluorine was in the 7th column, that would have been a -1. When we balanced these, we would have needed 2 fluorines in order to make a +2 and a -2, so we'd have gotten CaF2. Notice that's the same ratio as we got over here and as we have up here. Okay. Again, this section up here is your Lewis dot diagram and ionic bonding, and this is writing the formula for an ionic bond. All right, last example. If you'd like to try this one on your own, press pause on the video. Otherwise, you can continue watching and we will go through. So aluminum has 3 valence electrons. It's in group 3. Okay. Oxygen has 6 because it's in group 6. So if you notice, oxygen is the higher electronegative, aluminum is the lower, so aluminum is going to give to oxygen. Oxygen has 2 vacant spaces, so one of these is going to go to one space and one's going to go to another. So we will have 2 arrows, one taking this one to that spot, one taking this one to that spot. Okay, but if you notice, we still have 1 aluminum electron left over, so we need another oxygen. So we will take this aluminum now to one of the empty spaces on oxygen, and now we have another empty space on oxygen. So we'll add an aluminum. So we take one of our aluminums, because it's still the less electronegative than oxygen. Aluminum gives its electron to oxygen. Now we have aluminum with 2 extras. So we have to add another oxygen. So now we'll be able to finish, and one of these aluminums will go here, and one of the aluminum electrons will go here. Now everyone's satisfied. Everyone has a full valence shell. We do our double arrow. Again, remember we have to alternate. So we'll say oxygen with it now has all 8, and it gained 2, so it has a 2 minus charge. Aluminum, it lost 3, so it's a plus 3. Oxygen, minus 2. Aluminum, plus 3. Oxygen, minus 2. Again, alternating, we show that oxygen has its full 8. Aluminum has its full 8, but not in its original. We draw it as its original valence shell. Its original valence shell is now empty. This implies that the inner shell is now a full valence shell. Okay, so what ratio of aluminum and oxygen must there be in order to satisfy the rule of octet? Well, for every 3 oxygens, we have 2 aluminums. So every 2 aluminums, 3 oxygens. Again, if we went back to our naming, aluminum is in the 3rd column. That's a plus 3. Oxygen is in the 6th column. That's a minus 2. In order to balance this, we would need a plus 6 and a minus 6. So we get Al2O3. What is the sum of all the charges on the ions in each example above? Well, if you look at our previous example, we have -2 plus 3, -2 plus 3, -2. If we sum up all our negatives, that gives us a -6. If we sum up all our positives, we get a positive 6. The sum of that is 0. Okay, so if we look, we get a sum of 0. Why is that? Electrons are transferred between them to create charged ions. No electrons were added or lost from the systems, so the charges should cancel. I like to think of this as a bank account. Okay, so if I had $20 and I put $10 in a checking account and $10 in a saving account, I still have $20, right? Let's say I take $5 in my savings account and I put it into my checking account. I now have $5 in my savings account and $15 in my checking account, but I still have $20. Okay, so the total charge of the ions started off as neutral atoms, so they had a net charge of 0. When they transfer, one loses but one gains, so the net charge is still going to be 0. Okay? That's all we have for today. Again, remember that your test is next Tuesday, so come see me on Monday with questions. And also the Lewis dot diagram and ionic bonding worksheet that I attached to the email is your homework, and it will be due Thursday. That'll be the class we have after the test day. All right, enjoy your day.